The following is in the book on page 198.
Today, we are going to talk about the resting potential of neurons. There is a difference in the electrical potential between the outside of the membrane of the axon and the inside when the axon is not conducting an impulse. We will shortly see the axon to remember what it looks like. It is important to remember that there is a difference in the electrical potential between the outside of the axon's membrane and the inside. This difference in charges allows the membrane to conduct electrical potentials. At no point can the electrical potential across the axon's membrane be zero. If it reaches zero, the neuron dies. The outside of the membrane is positively charged and the inside is negatively charged. As we see here, this is the outside where the plus signs indicate positive charge. And here is the inside where the minus signs indicate negative charge. Here is an example of a neuron. And here we see the axon with its elongated shape, which allows it to carry electrical impulses over distances. Electrical potential is found across the membrane of the axon. The membrane of the axon is partially permeable. When we say a membrane is permeable, that means it's not completely sealed. It allows certain particles to cross from the outside to inside or from inside to outside. In the case of the axon, these particles are ions. And when we talk about ions crossing the membrane of the axon, we specifically mean sodium and potassium. Ions can go inside and outside the axon in a controlled manner. When the axon is not conducting a nerve impulse, we say it is at rest. To explain how electrical potentials across the membrane form, we need to explain pumps. Pumps are like the gates found on membranes, and they allow certain ions to pass through them. The most important pump here is the sodium-potassium pump. A sodium-potassium pump uses energy to move sodium to the outside and potassium to the inside. This energy is provided from the food we eat, and one of its uses is to allow sodium-potassium pump to work. This causes more potassium to be on the inside than on the outside, creating a gradient. When we create a gradient, we create a place of high concentration of one substance and leave an adjacent place with low concentration of that substance. Aside from pumps, we also have channels. Unlike pumps, channels allow ions to move freely across them without the need for energy. At rest, the membrane is almost impermeable to sodium ions and almost freely permeable to potassium ions. When there is no electrical impulse, sodium channels are closed, while potassium channels are open. This allows potassium ions to move according to their gradient. This means they will go from places of high concentration to places of low concentration. Potassium ions travel down their gradient. They will leave the inside of the axon through the potassium leak channels to the outside. Here are the potassium leak channels. As mentioned, they are always open even when there is no electrical impulse. We can see potassium ions leaving from the inside to the outside down their gradient. At rest, there will always be more sodium on the outside than on the inside. The sodium-potassium pump will create a gradient of potassium, which will allow potassium ions to exit to the outside through potassium leak channels that are always open at rest. This makes the outside of the membrane positively charged and the inside negatively charged. Sodium is at higher concentration on the outside and is unable to go to the inside down its concentration gradient because its leak channels are closed. This is unlike potassium ions whose leak channels are open, which allows them to travel down their gradient. This is what causes the difference in electrical charges across the membrane. We call this the resting potential, and it is measured at -70 millivolts.